Hey everyone, in this video we're going to talk about linear regression. This is going to be a nice application for linear functions. So the core idea is the following. Suppose that we had a data set which we could graph, and it's going to appear like the following. Right now, the data doesn't really seem to have any kind of rhyme or reason, right? There's no real shape or trend that any of these data points are following. But what if our data set was more detailed and we had a lot more points? At this point, we can kind of see a shape emerging. We would actually say that this set of data has a linear trend. Obviously, not every data point is falling on a straight line, but they're sort of tending to that line. And really, that's one of the big things that happens in statistics and applied math, is you're trying to figure out what kind of shape or trend does your data set have. So if we're going to decide that this data point falls on a linear path, the question is, what line? What linear function best models or represents this data? Is there a mathematically best fitting line? If it is, what does that look like and how is it found? So just to make sure we're all on the same page in terms of terminology, whenever you use the word model, we're talking about a function that can be used to predict future trends. So to find the mathematically best fitting line, we're going to use something known as the least squares method. The goal here is to construct the mathematically best fitting line to a set of given data points. So let's look at a set of 4 points that are very specific here. We have 114, 318, 621, and 1025. Now in real life, data sets are a lot larger, and you've probably heard the term big data before. So a set of 4 points isn't a very interesting one in real life, but it's going to be nice for the sake of our example, because the least squares method, while it's very nice, does take a lot of computations, so we're going to keep the points to a minimum. The notes that correspond with this video uses these points and others. Again, because this is a lot of computations, we're trying not to make this too overwhelming, especially with the computations. So once you're done watching this video, go look at the corresponding notes and see the example that has these data points and more. So again, what we're after is a linear function that best fits all of these 4 points. Now these 4 points kind of fall on a curve more than a line, but we can clearly see that they have a somewhat linear trend. And a linear function might be the best thing to model them. So if I have a linear function, I need to find its slope and I need to find its y-intercept. And that is what the least squares method is going to do for us, is find us these values through some intricate steps. So the first step is the following. We're going to find these symbols that we call x bar and y bar, and these are just going to be the averages of the x and the y coordinates. So our x coordinates being 1, 3, 6, and 10, let's take their average, or rather their sum, and divide it by 4, and we get a value of 5 for x bar. Similarly, we're going to take the y values, 14, 18, 21, 25, add them together and divide by 4 to compute their average, and we'll see that in this case, y bar is equal to 19.5. Next, using the x bar and y bar values that we just computed, we're going to compute delta x and delta y. Now the symbol capital delta here, the Greek letter delta that is, typically means the change of. And if you go on to take Calculus 1, you'll see the symbol show up a few times and it will carry the same meaning. So as is defined, delta x is defined as taking each x value and subtracting x bar. Really what this is trying to gauge is how far is each x coordinate away from its average. Delta y is computed in the same way. And at this point, it's good to start doing xy charts to catalog all of our values. At this point, it's going to be good to catalog all of our values. Let's write down our x and y bar at the top, and then let's do an x and y chart for all of our coordinates. Now we're going to compute delta x. So I'll run through all of my x coordinates and subtract the average. So I get delta x values of -4, -2, 1, and 5. In a similar way, I'll compute my delta y value. I'm going to run through all of my y coordinates and subtract y bar. This is going to give me -5.5, -1.5, 1.5, and 5.5. Applied problems like this typically are going to reveal a lot of non-integer values, and that's okay. It doesn't mean that we've done anything wrong. It just means that we have to be careful about the values we're computing because, like I said before, there are a lot of computations. So XY charts and pretty much a chart for any computed value is going to be essential for our process and for our organization. Okay, now we need some notation. The Greek letter capital sigma, when it shows up, typically means the sum of. And our textbook and our notes are going to use this symbol for the next things that we'll compute. So our third step, we need to compute the sum of all of the delta x and delta y products and the sum of delta x squared. Like I said, we're going to have a lot of XY charts to help us do these. But when I see the sum of stuff, it just means that I'm taking the sum of a whole bunch of terms. So I'm going to use another chart. In one column, I'm going to compute all the products of my delta x and delta y values, and then I'll compute the value of delta x squared. So all of our delta x times delta y values are going to be listed as follows, and all of our delta x squared values are going to be listed as follows. So everything in the delta x, delta y column, all I'm doing is just going through each row and multiplying those values. So 4 times negative 5.5 is what's giving me 22. Negative 2 times negative 1.5 is giving me 3, and so on. And the same thing applies for all of my delta x squared values. Now to compute these sums, I'll just take the sum of that left column, which is going to give me 54, and the sum of that right column, which is going to give me 46. So there you go. I have my sum of delta x, delta y, which is 54, and my sum of delta x squared values, which is 46. Alright, and y'all are in luck because we are finally at the fifth and final step for computing our mathematically best fitting line. We have everything we need to construct our m value, the slope, and our y-intercept value, b. The slope of this line is given by the following formula. M equals to the sum of delta x times delta y divided by the sum of delta x squared. On the previous slide, we found that those are going to be 54 and 46 respectively, which when we reduce that down, we get the value of 1.174, and we have the slope of our best fitting line. Next is our b value. This is computed by the formula b equals to y bar minus m times x bar. When we plug in all of the values that we found, we are going to end up with the value 13.6305. And like I said, this is the fifth and final step. We now have the information for our best fitting line. This is going to be given by the function f of x equals 1.174x plus 13.6305. Again, I do recommend you going to the notes to look at the example that has more data points. It does follow the same number of steps, it just has more computations. And that would have been a little bit too much for the purpose of this video, but it's okay for the notes. But now a question that we can ask is how good does this line actually fit? Because maybe you have a data set that's kind of linear in its appearance, but it only goes so far. We can actually get a percentage that tells us how well our line is fitting. And we call this the correlation coefficient. And we can compute this using all of our gathered data so far with one additional term, sigma of delta y squared. So we can make another xy chart and get our delta y squared values, which are going to be listed as follows. When I take that sum, we'll find that I get a value of 65. Then we are going to compute the correlation coefficient, typically denoted by lowercase r, and it's going to be given by the formula, the sum of delta x divided by delta y, all divided by the square root of the sum of delta x squareds times the sum of delta y squareds. Again, we have all these values, and now we have the new sum of delta y squareds, and we throw all these values together into our correlation coefficient formula, we're going to get a value of 0.988. Now again, what does this value mean for us? The word correlation coefficient basically says how well our data fits the line that we just constructed. Because maybe you have just a very weird data set and no straight line really is going to fit it super well. But a score of 0.988 is very, very strong. Basically that correlates to a 98% fitting rate. If you go on to take statistics in the future, which I highly recommend, you'll talk more about this type of concept as well as things like adjusted R-square values that tell you how good your line fits. But for now, we just introduced the correlation coefficient and the process of the least squares method.